Introduction and Global Reach Overview. Welcome to our comprehensive exploration of Azure ExpressRoute Global Reach. This revolutionary technology transforms how we connect multiple on-premises sites through Microsoft's global backbone infrastructure. Traditional site-to-site connectivity required complex VPN tunnels or expensive MPLS networks. Global Reach eliminates these challenges by allowing direct connectivity between ExpressRoute circuits in different locations. Think of it this way. Instead of routing traffic from your New York office to London through your Azure virtual networks, Global Reach creates a direct, private connection using Microsoft's backbone. This means lower latency, higher throughput, and simplified network architecture. The key benefits we'll explore include direct site-to-site connectivity without hub routing, leveraging Microsoft's global backbone infrastructure, simplified network topology and management, enhanced security with private connectivity, and reduced latency between global locations. This presentation covers the complete implementation from planning through deployment, with real-world examples using New York and London as our primary sites. Global Reach Architecture. Let me walk you through the architecture that makes Global Reach so powerful. The diagram shows how Microsoft's backbone becomes your private network infrastructure. In traditional setups, traffic from New York to London would flow through ExpressRoute to Azure, then back through another ExpressRoute circuit. With Global Reach, we create a direct connection between circuits. The key architectural components include ExpressRoute circuits, which provide your dedicated connections to Microsoft, the Microsoft backbone, the global infrastructure connecting regions, the Global Reach connection, the logical link between your circuits, and BGP sessions, for exchanging routes between your networks. Notice how this creates a hub-spoke topology with Microsoft's backbone as the hub. Your on-premises networks become spokes that can communicate directly through the Microsoft network. This architecture eliminates the need for complex routing through Azure virtual networks while maintaining the security and performance of private connectivity. Prerequisites and requirements. Before implementing Global Reach, we need to understand the specific requirements and how they differ from standard express route connectivity. The table shows critical prerequisites. Notice that both circuits must have private peering configured. This is the foundation that Global Reach builds upon. Geographic considerations are crucial. Both circuits must be in Global Reach supported regions, and there are specific requirements for cross-geographic connections. From a technical perspective, you need standard or premium circuits only. You need a minimum of 50 megabits per second bandwidth, with the maximum limited by the smaller circuit. Unique ASNs are required for each location, and you need non-overlapping subnets. Security requirements include proper authorization key management and RBAC permissions for Global Reach operations. The comparison with traditional connectivity shows significant advantages in complexity reduction and performance improvement. Multi-site connectivity design. Designing multi-site connectivity with Global Reach requires strategic thinking about your network topology. The diagram illustrates different approaches you can take. The hub-spoke model designates one location as the primary hub, in our case, New York. All other sites connect to this hub, creating a centralized routing architecture. Regional clustering is particularly effective for global organizations. You might have an Americas hub in New York as primary, an EMEA hub in London as regional, and an APAC hub in Singapore for future expansion. Each approach has trade-offs. Hub-spoke minimizes the number of Global Reach connections but creates dependency on the hub. Mesh topology provides redundancy but increases complexity and cost. Consider bandwidth requirements carefully. The hub location needs sufficient capacity to handle traffic from all spokes, while spoke-to-spoke traffic still flows through the hub in this model. For our implementation, we're using New York as the primary hub with London as a regional hub, allowing for future expansion in both regions. Network topology planning. Strategic topology planning ensures your Global Reach implementation scales effectively and meets performance requirements. The connection patterns shown represent different strategic approaches. The star pattern centralizes everything through one hub, while the regional clustering approach distributes load across geographic regions. Key planning considerations include latency requirements where hub placement affects global latency, bandwidth distribution where hub circuits need higher capacity, redundancy planning with secondary hubs for failover, and growth accommodation for easy addition of new sites. Our recommended approach uses regional hubs to minimize latency and distribute load. New York serves America's traffic while London handles EMEA requirements. This topology planning directly influences our circuit sizing decisions. For example, New York gets 10 gigabits per second as the primary hub, while London gets 5 gigabits per second as a regional hub. The pattern also prepares us for future expansion into APAC regions without requiring architectural changes to existing connectivity. Primary circuit creation, New York. Now we move into implementation, starting with creating our primary express route circuit in New York. This circuit will serve as our America's hub. Let me explain each parameter in the command. The location, East US, provides optimal connectivity for our New York office, and Equinix is our chosen provider for reliable East Coast connectivity. The bandwidth selection of 10 Gbps reflects our hub role. This circuit will carry traffic not just for New York, but potentially for other America's locations that connect through this hub. Key parameter decisions include the SKU tier as premium for global connectivity support, the billing model as unlimited for predictable costs, a resource group dedicated to express route resources, and tags for environment and project identification. The command creates the circuit foundation, but remember, this just reserves the circuit. We still need to configure peering and establish the physical connection with our provider. After creation, you'll receive a service key that you'll provide to Equinix to establish the physical cross-connection in their facility. Secondary circuit creation, London. Our London circuit serves as the regional hub for EMEA operations. Notice the strategic differences in this configuration compared to New York. We're using BT as our provider in the UK West region. This choice optimizes for London connectivity and provides different provider diversity from our New York circuit. The 5 Gbps bandwidth reflects London's role as a regional hub rather than the global primary hub. This right sizing helps manage costs while providing sufficient capacity for EMEA traffic. Important configuration notes include provider selection, where BT offers excellent UK connectivity, location strategy, with UK West for London optimization, capacity planning, with 5 Gbps for the regional hub role, and resource grouping, in the same group for centralized management. The premium SKU is essential here. It enables global reach connectivity between regions. Standard SKU circuits cannot participate in inter-region global reach connections. Like the New York circuit, this command creates the logical circuit that you'll need to activate with BT through their provisioning process. Private peering configuration. Private peering is the foundation that enables global reach. Without properly configured private peering on both circuits, global reach connections cannot be established. Let me walk through the critical parameters. The VLAN IDs must be unique across your entire ExpressRoute deployment. We're using 100 for New York and 200 for London to maintain clear separation. The subnet assignments are crucial for global reach. The primary subnet uses a 30 network for the main BGP session. The secondary subnet uses a 30 network for the redundant BGP session. ASN selection requires unique private ASNs for each location, and the VLAN strategy needs non-overlapping IDs across circuits. Notice we're using private ASN 65001 for New York and 65002 for London. These ASNs will be used in BGP routing and must be unique across your global reach topology. The subnet choices ensure no IP overlap between locations, which is critical for successful global reach operation. Each circuit gets its own 30 subnets for the BGP sessions with Microsoft. Both circuits must complete this peering configuration before we can establish global reach connectivity between them. Authorization keys are the security mechanism that controls which circuits can establish global reach connections. This is a critical security feature that prevents unauthorized connections. The process works like this. The circuit owner generates an authorization key and shares it with the administrator of the remote circuit. Only someone with both the circuit ID and the valid authorization key can create the connection. Key management best practices include limited lifetime, meaning keys expire automatically for security. Single use, where each key is consumed when used. Secure distribution, which involves sharing keys through secure channels. And documentation, to track which keys are used for which connections. In our example, we're generating a key on the New York circuit that will be used to authorize the connection from London. The key name should be descriptive to help with management. After running this command, you'll receive an authorization key that looks like a GUID. This key, along with the circuit resource ID, is what you'll use when establishing the global reach connection. Remember to treat these keys like passwords. They provide access to your ExpressRoute circuit for global reach connections. Global reach connection establishment. This final step brings everything together by establishing the actual global reach connection between our New York and London circuits. The command runs from the London circuit perspective, using the authorization key we generated from New York. This creates the logical connection that enables direct communication between our sites. Critical parameters explained include the address prefix, which is a /29 subnet for the global reach connection, the authorization key, which is the security token from the remote circuit, the peer circuit, which is the full resource ID of the New York circuit, and the connection name, which is a descriptive identifier for management. The /29 subnet, specifically 10.10.10.0/29, is used exclusively for the global reach connection between these two circuits. This subnet must not overlap with any other networks in your topology. Once this command completes successfully, BGP sessions will be established between your circuits, and you'll be able to route traffic directly between New York and London through Microsoft's backbone. You can verify the connection using a Z-Network Express route peering connection show and monitor BGP route advertisements to ensure proper connectivity. Let's discuss BGP route configuration and advertisement. Now that our global reach connection is established, we need to configure BGP routing to ensure proper traffic flow between our sites. The beauty of global reach is that BGP sessions are automatically established between your circuits, but you need to configure route advertisements to control which networks are accessible. Key BGP concepts for global reach include route filters that control which routes are advertised and received, AS path prepending to influence routing decisions for traffic engineering, community strings to tag routes for policy application, and route maps for complex routing policies and transformations. Our New York circuit using ASN 65001 will advertise 10.1.0.0/16, while London using ASN 65002 advertises 10.2.0.0/16. This creates clean, predictable routing between sites. Route verification is crucial. You'll want to check that routes are being properly advertised and received on both circuits using the verification commands that are shown. Remember that BGP convergence can take a few minutes, so patience is key when validating the routing configuration. Connection status verification and monitoring. Continuous monitoring of your global reach connections is essential for maintaining reliable connectivity between your sites. The verification commands I'm showing provide comprehensive insight into connection health. The connection status should show connected for successful establishment. Key monitoring points include BGP session state, which should be established for both primary and secondary, route advertisements to verify expected routes are being exchanged, traffic flow to monitor actual data transmission between sites, and latency metrics to track performance improvements from global reach. The metrics display shows the kind of performance improvements you can expect. Our New York to London connection shows 95 milliseconds latency, significantly better than routing through Azure Virtual Networks. Bandwidth utilization monitoring helps with capacity planning. We're seeing 2.3 Gbps usage on our 5 Gbps London circuit, indicating good utilization without congestion. Set up automated monitoring and alerting for these key metrics to proactively identify and resolve connectivity issues. Advanced route filtering and traffic engineering. As your global reach topology grows, sophisticated route filtering and traffic engineering become essential for optimal performance. Route filtering allows you to control exactly which networks are accessible between sites. This is crucial for security and compliance requirements. Traffic engineering techniques include AS path prepending to make certain paths less preferred, local preference to influence outbound routing decisions, MED attributes to signal preferred entry points to your AS, and community tagging to apply consistent policies across multiple routers. The example shows filtering sensitive development networks at 10.1.100.0/24 from being advertised to London, while allowing production networks at 10.1.0.0/20 to be shared. Traffic engineering becomes especially important when you have multiple paths between sites or when implementing backup connectivity through different providers. Consider implementing route dampening to prevent flapping routes from causing instability in your global network topology. Troubleshooting global reach connectivity. When global reach connections experience issues, systematic troubleshooting is essential for rapid resolution. The most common issues fall into 4 categories shown in the troubleshooting grid. Let me walk through each category in detail. BGP session issues often stem from mismatched ASN configurations, incorrect subnet assignments, authorization key problems, and provider provisioning delays that can prevent proper session establishment. Route advertisement problems typically involve filtering misconfigurations or overlapping network announcements that create conflicts in the routing table. Connectivity issues can range from physical layer problems with your express route provider to Microsoft backbone issues that require support escalation to resolve. Performance degradation might indicate bandwidth saturation, suboptimal routing paths, or increased latency due to routing changes in the Microsoft backbone. The diagnostic commands shown provide detailed insight into each layer of the connectivity stack, from physical link status through BGP routing table contents. Security and compliance considerations. Global Reach introduces specific security considerations that require careful attention in enterprise environments. The security controls shown represent best practices for Global Reach deployments. Let me explain each control in detail. Network segmentation ensures that global reach connections don't inadvertently expose sensitive networks. Use route filtering to control exactly which subnets are accessible across sites. Access control implementation includes RBAC policies to limit who can create and modify global reach connections, authorization key management for secure generation and distribution lifecycle, audit logging to track all configuration changes and access, and compliance reporting to document network topology for auditors. Encryption considerations are important. While global reach traffic traverses Microsoft's backbone securely, you may need additional encryption for highly sensitive data transfers. Monitor for unauthorized route advertisements or unexpected traffic patterns that might indicate security breaches or configuration errors. Regular security reviews should include global reach topology assessment, authorization key rotation procedures, and validation of route filtering effectiveness. Performance optimization and best practices. Achieving optimal performance for global reach involves understanding both technical configuration and operational best practices. The optimization strategies shown can significantly improve your global network performance. Let's detail each approach systematically. Bandwidth optimization starts with right-sizing your circuits. Our New York hub at 10 gigabits per second provides headroom for growth, while London's 5 gigabits per second matches current regional needs without over-provisioning. Key optimization techniques include circuit placement, which means selecting locations closest to your offices, provider selection, which involves evaluating latency, reliability, and local presence. Redundancy design, which is about planning for circuit and provider failures. And traffic patterns, which helps you understand and optimize for your actual usage characteristics. Regional clustering reduces latency by keeping traffic within geographic regions when possible, while still providing global connectivity when cross-regional communication is needed. Quality of service configuration ensures that critical applications get priority during periods of high utilization across your global topology. Regular performance reviews help identify usage trends and plan for capacity upgrades before they become bottlenecks that impact user experience. Cost management and optimization. Understanding and optimizing global reach costs is crucial for sustainable global connectivity strategies. The cost breakdown shows the major components of global reach expenses. Notice how circuit costs dominate the monthly spend. This is where optimization efforts should focus primarily. Cost optimization strategies include right-sizing circuits to match bandwidth to actual needs plus reasonable growth projections, regional consolidation using hub-spoke to minimize total circuit count, provider negotiation to leverage multi-site deployments for better rates, and usage monitoring to track actual utilization versus purchased capacity. Our example shows $8,500 monthly for the complete New York-London global reach setup. While this seems expensive, compare it to alternatives like MPLS networks or multiple VPN solutions with their associated complexity. The global reach connection fee of $150 per month is minimal compared to circuit costs, making it very cost-effective to add connectivity between existing ExpressRoute circuits without additional infrastructure. Consider reserved instances for long-term deployments to reduce circuit costs by up to 38% with annual commitments, providing significant savings for stable deployments. Regular cost reviews should evaluate utilization trends and identify opportunities for circuit optimization or provider contract renegotiation. Scaling to multiple regions. As your organization grows globally, scaling global reach requires strategic planning for optimal topology and performance characteristics. The multi-region topology shown demonstrates how to expand from our initial New York-London setup to include APAC operations with Singapore as the regional hub. Scaling considerations include hub selection, which means choosing locations with optimal geographic coverage for each region, bandwidth planning, where hubs need capacity for aggregated traffic from multiple spokes, provider strategy, to maintain diversity across different geographic regions, and route optimization, to minimize unnecessary hub traversals that add latency. The regional clustering approach scales efficiently. Each region has its designated hub, and inter-region traffic flows through hub-to-hub connections. This minimizes the total number of global reach connections needed. For a 3-region topology, you need only 3 global reach connections, between New York and London, London and Singapore back to New York, rather than 6 connections for full mesh connectivity. Consider future expansion when designing your initial topology. It is much easier to add spoke sites to existing regional hubs than to restructure your entire global architecture later. Automation becomes critical at scale. Use infrastructure as code principles to deploy and manage multiple circuits consistently across regions. Disaster recovery and high availability. Building resilient global reach connectivity requires careful planning for various failure scenarios and comprehensive recovery procedures. The high availability design shown demonstrates how to build multiple layers of redundancy into your global topology. Each layer protects against different types of failures. Redundancy strategies include dual circuits with primary and backup ExpressRoute circuits per location, provider diversity using different carriers for redundant paths, geographic distribution with alternative hub locations for regional backup, and automatic failover using BGP-based path selection for seamless transitions. Circuit-level redundancy uses BGP path selection to automatically route around failed circuits. Configure different local preferences to control primary versus backup path selection during normal and failure conditions. Regional redundancy protects against broader outages by providing alternative hub locations. For example, Frankfurt could serve as a backup hub to London for EMEA operations during regional issues. Your disaster recovery procedures should include both automated failover capabilities for common scenarios and manual intervention steps for complex failure situations that require human decision-making. Regular DR testing validates both your redundancy design and operational procedures. Test different failure scenarios quarterly to ensure your team is prepared and systems respond correctly. Operational excellence and future planning. Achieving operational excellence with global reach requires establishing comprehensive monitoring, automation, and governance practices for long-term success. The operational framework shown represents industry best practices for managing global ExpressRoute deployments at enterprise scale. Key operational excellence pillars involve automation, using infrastructure as code for consistent deployments across regions, monitoring, for comprehensive visibility into performance and health metrics, documentation, with current topology diagrams and standard procedures, and change management, with controlled processes for modifications and updates. Future planning considerations include emerging technologies like SD-WAN integration for hybrid connectivity, IPv6 support for next-generation addressing, and integration with Azure Virtual WAN for simplified management of complex topologies. Establish regular architectural reviews to evaluate new Azure networking capabilities and assess their fit with your existing global reach topology and future requirements. Consider the evolution toward Azure Virtual WAN, which provides simplified management and additional features for global connectivity scenarios while building on your global reach foundation. Your global reach implementation provides the foundation for advanced networking scenarios like multi-cloud connectivity and edge computing integration as your organization's needs evolve. Congratulations on completing this comprehensive global reach implementation guide. You now have the knowledge and tools to deploy, manage, and optimize global reach for enterprise-scale global connectivity with confidence.